and we will operate or we will run that machine in motoring control. Motoring control in the sense the first quadrant. So, so what we do is that we will take the separate like serial DC motor and we will operate that machine in the motoring control. Motoring control in the sense, the forward motoring. That is the first quadrant. Okay. So in the first quadrant we will operate. So the circuit diagram we draw here. I hope you remember the when you want to operate in the first quadrant, what is the circuit diagram? I hope you remember that. Okay, so we just draw that here. This one. There is no difference between what we did earlier and what we are going to do now. Okay, so more or less it is same. Except here we gave the name here motor is there. Okay, uh, this is EA. Now you have separate accelerated DC motor. This is EB, RA, LA. The voltage, output voltage here is E naught. Okay. The current flowing here is EA. IA is the current flowing here. Okay, so what we do here is that the same thing that we close the switch, that is switch is on. If the switch is on, I hope you remember the equivalent circuit of the chopper. Okay, the switch is closed and the diode becomes reverse bias. This is IA, where the voltage here is E naught and the voltage here is EA, RA, LA, EB. So applying KVL in this circuit diagram, we will see EA is equal, E naught is equal, okay, A is equal to E naught is equal, IA, RA plus LA, D, IA by dt plus EB. This is when the switch is on. So I will say between the duration 0 less than or equal to T less than or equal to T on during this duration. Okay. So what is EA here? What is E naught we got here? EA. Okay. Now when the switch is off, which is off in the sense the time duration is T on less than or equal to T less than or equal to capital T total time period. So in that case when the switch is off, you know the diode becomes forward bias, so it becomes short circuit. IA. Okay. So plus minus. So E naught is equal to 0 because the diode is forward bias. What is the KVL equation you will get here? The KVL equation here will get is that IA RA plus LA D IA equal to D plus EB is equal to 0. Okay, now from this, what is the average voltage? What is the average voltage? So, see, we have already done this derivation. So, I will write directly, it's better. What is that derivation we got is that E naught is equal alpha into EA. What is alpha? Alpha is equal T on by total time. Okay. So, this is E naught of voltage. Okay. And then, what's next now? What's next is that once we got this, so we got the answer for the output voltage. We got the answer for the output voltage. So now, see, we will recall this equation. Input voltage to the armature is nothing but EB plus IA RA. This is your equation of the motor. This is the equation for the motor equation. So now, how do you write EB? I can write EB as some constant K into omega. This is back EMF in terms of omega. Similarly, how can I write this is separate electric DC motor? So how can I write electromagnetic torque E? I can write K into IA. These are the three equations we have. Using these three equations, what we do is that what we do here is in these three equations is that okay, so we substitute that. Nothing else is there. We substitute that here. So E naught in place of E naught, I will write alpha EA. That is equal to in place of EB, I will write K omega plus in place of IA, I will write from the torque equation PE by K into RA. Okay. So from this, what is omega from this? Omega is equal to alpha EA by K alpha EA by K minus PE by K square into RU. This is the equation. This is the equation we got. This is the equation we got. There is a relationship between speed and torque. Relationship speed and torque. So now we'll draw the graph. What is the graph you will get here in that? So what is the graph you will get if I take so here is T electromagnetic and this is omega. Then yeah, we will take first T is equal to 0. If I take T is equal to 0, we start with electromagnetic torque is equal to 0, then we get omega value first for one value of alpha. Okay, then if I go on increase TE, you will find out that it's decreases. So you will get a graph like this, something like this, decreasing, linearly decreasing. So this is for one value of alpha. So if I increase the value of alpha, we will find out the graph goes up. So here alpha increasing. Here alpha increasing. Here alpha increasing. So this is the relationship between speed and torque. So we got this relationship. So that's it. So this is about the chopper control of your separately excited DC motor in the forward motoring condition. So now we'll solve a numerical problem here, so that we will understand more about this particular method. Yeah, this is the numerical problem. Okay. Now you see. With this, a DC shunt motor takes a current of 50 ampere on a 440 volt supply, runs at a speed of 1000 rpm with an armature resistance of 0.5 ohm and field resistance of 100 ohm. Okay. So you see here, first of all, he has given the data related to DC motor, DC shunt motor. A DC shunt motor takes a current of 50 ampere on a 440 volt supply. So the supply voltage is 440 volts and the current is 50 ampere at the speed of 1000 rpm. That's important. With an armature resistance of 0.5 ohm and field resistance of 100 ohm. Okay. Then what's next now? A chopper is used to control the speed of the motor. A chopper is used used to control the speed of the motor in the range of 400 to 800 rpm. So you are using a chopper having a constant torque. Okay, so without changing the torque, he's saying that we will control the speed from 400 to 800 rpm using a chopper. The on period of the chopper is 2 milliseconds. That's important. With the field supply voltage from 440 volts. Okay, that is there. Okay, determine the range of frequencies of the chopper. Okay. So he is asking first, what is the question? Only one question is there. What is the range of frequencies of the chopper? So range of frequencies of the chopper in the sense. First of all, why do you change the frequency? He said that the on time is 2 milliseconds. That's important. So I think he has fixed the on time as 2 milliseconds. Okay, when he fixed the on time as 2 milliseconds. Okay, see the class A chopper, that is this first quadrant chopper. So what you find out in the first quadrant chopper is that one important thing you must understand in the first quadrant chopper. What is that thing? Is E naught is equal alpha EA. This is the output voltage of the first quadrant chopper. What is alpha here? Alpha is equal T on by T. So now you want to control, see here, you want to control E naught, then what you want to control? You have to control alpha. You want to control alpha, you have two options. Either you control T on or you control capital T. In the problem, he said that T on is 2 milliseconds. So I think it is 2 milliseconds only. Then how do you control alpha? Then what is the only option it you have now? The only option it has is that you control capital T. That is the time period you control. So controlling time period is nothing but what? Frequency. So for different frequencies, because 1 by T you can write it as F. So for different frequencies, you will have different values of alpha. If you have different values of alpha, you will have different values of E naught. If you have different values of E naught, then you will have different values of speeds. That's the logic here. Okay. So the question, as per the question, he is asking the frequency, range of frequency. Okay. So how do you find the range of frequencies? Is that it means he is asking the frequency at 400 rpm. He is asking the frequency at 800 rpm. Because the range of speed he said that the speed range is 400 to 800 rpm. So as the speed is 400 to 800 rpm. So one thing we will do here is that okay. So we will use, see, you want to find out the frequency. So your only thing is that you find out where is the frequency first of all. So here there is a frequency there. So alpha is equal T on into F. I will write because 1 by T is F. So here you have F. So what is the value of F here? F is equal to alpha by T on. Now, what are the things that you don't know here? What are the things that you don't know here? So he has given 2 milliseconds. Okay. So we are given 2 milliseconds. So it means T on is known value. How much it is T on? I will write here 2 milliseconds. 2 into 10 power minus 3 seconds. Okay. Now alpha you don't know. So how do you find out alpha? So if you find out alpha, then you can do that. Where can you find out alpha? Yes, there is a equation here. E naught is equal to alpha EA. This is here. This equation here. Alpha is equal to E. So from this, what is alpha? Alpha is equal to E naught by EA. So to find out alpha, I will have to use this one, E naught by EA. So how can I find out one by one? So one by one, what is EA first of all? What is E naught? E naught. What is EA? EA. In the problem, I think he has given EA is nothing but a supply voltage. How much supply voltage you see? You read the statement of the chopper. A chopper is used to control the speed of the motor in the range of 400 to 800 rpm, having a constant of the on period of the chopper is 2 milliseconds, which is field supply voltage from okay. So the supply voltage for the chopper is 440 volts. Okay, so EA is equal to 440 volts. Okay, we got EA. Then what we don't know here? We don't know what is E naught. E naught we have to find out. So how do you find out E naught? What is E naught? E naught is the output voltage of the chopper or input voltage to the motor. Output voltage of the chopper or input voltage to the motor. So what is the input voltage to the motor? Generally, we have the equation EB plus IARA. That's it. We have this equation. So as we have this equation, so to find out E naught, we have to find out all these three. One by one we'll see here. First of all, what is RA? RA, he has given RA in the problem, I think. So what is the RA value in the problem he has given is that 0.5 ohm. So RA value is 0.5 ohm. Then, how do you find out IA? What is the logic to find out IA? Okay, so this is also one of the important things. So then we will see that is there he has given any data here. Okay, so yeah, one thing he said that is yeah, please see here. One important statement he has given: a chopper is used to control the speed of the motor in the range of 400 to 800 rpm, having a constant torque. So he said the torque is constant. So the torque is constant in the sense if the torque is constant, okay, if the torque is constant, its armature current you can consider as constant. So what is constant in this is what is its armature current? You go back to the DC shunt motor data. A DC shunt motor takes a current of 50 ampere on a 440 volts, runs at a speed of 1000 rpm. So the armature current is 50 ampere. The armature current is 50 ampere, and he said the torque is constant. So I will consider this armature current whichever he has given is constant. So armature current is constant. So torque is constant in the sense I will consider armature current is constant. So IA also I know how much it is IA. IA is equal to 50 ampere. Now what is left now? EB. So we have to find out what is EB. What is EB? EB is the back EMF. Back EMF depends upon what? Back EMF depends upon speed. So I will write here back EMF. It depends upon speed. Okay. Then what we do is that now. So he is asking the speed range is what is the speed range? 400 to 800 rpm. This is the speed range. So first I will take one speed, then I will take the next speed. So for the first speed I will find out the frequency, then the next speed I will find out the another frequency. So first speed that is 400 rpm. So at this speed we will find out the frequency. So at this speed, what is the back EMF? We will have to find out. That is the question now. So what is EB at 400 rpm? This is the question now left. How do you find out this? Because you have to find out the frequency at 400 rpm. So definitely EB you have to find out at 400 rpm. So to find out EB at 400 rpm, we will do one thing. First, we will find out EB at 1000 rpm. Why EB at 1000 rpm? Because you see the data of DC shunt motor. What is the data he has given? DC shunt motor runs at a speed of 1000 rpm. Runs at a speed of 1000 rpm. So the motor runs at a speed of 1000 rpm. At that speed, the supply voltage is 440 and the current is 50 ampere. So we will use this data and we will find out the back EMF at 1000 rpm. So EB at 1000 rpm is equal. I will write here E naught minus IA RA. So E naught in the sense I will tell you already. E naught is what is the E naught here? E naught is nothing but the output voltage of the chopper or input voltage to the motor. So now the data rated values has given it is 440 volts minus IA is 50 ampere into 0.5. So the answer you will get here 400 minus 15 into 25, 25 into 415 volts. 415 volts is the back EMF at which speed 1000 rpm. Now we have to find out the back EMF at 400 rpm. 400 rpm. So 400, how do you find out the back EMF? If you know the back EMF at 1000 rpm, we have this equation EB proportional to N. So we will take this thing that EB at 1000 rpm is equal to EB at 1000 rpm into what can you write? 400 by 1000. Yes, you can write like this. In that case 450 into 400 by 1000 into 400 by 1000. So 166. 1000 if you do 166. So you got the answer 166 volts. So the back EMF for 400 rpm is 166 volts. So we will use this 160 volts here. Here we will use. So then what is E naught? You will get in this case E naught is equal back EMF. How much you got? 166 plus 50 into 0.5. So 25 plus 166. 190. So 191 volts. So we got 191 volts. So then we will substitute here. So E naught we got 191 divided by EA is 440. Then we will get the value of alpha. What is the value of alpha then?
Sir,
Please.
sir, in the case of rated speed, we take E naught is equals to EA, sir. Why, sir?
E naught is equal to, please tell,
E,
EA.
yes, sir.
Yeah, see here, why we have taken like this is that, see, it is the data of the DC motor. One thing you must understand is that it is the data of the DC motor. So already he has given one particular data of the DC motor. What is that data? And now why I have taken EA is that, see, he said himself, you see this now. The chopper, the chopper input voltage is how much? 440 volts. Am I correct or not?
Yes, sir.
Okay, chopper input voltage is 440 volts, and at the same time, what is the rated voltage of the motor? Please see this in the data. As per the data, we have to go. In the data, rated voltage of the motor is also 440 volts, whereas the chopper input voltage is also 440 volts. So that is as per the data. We cannot do anything. For example, if it is 440 volts and it is some other voltage, then in that case we will take 440 volts only, not this voltage. You understand now? So here we did not take. Let me clarify this. We did not take. Sorry, I will write here. Okay, I will write here EA, so that, yeah. Okay, write this one EA or what? I cannot write EA also. Yeah, it is E naught only. So E naught in the sense, I will write here E naught is the uh, input voltage to motor. Please see here. Here there is, we did not take any kind of assumption. In the data itself, he has given that the rated voltage of the motor, and the input voltage to the chopper, both he has given 440 volts. So that's the reason that we got 440. Understood?
Yes, sir.
Okay. Okay. Thank you. So then we got the value of alpha. So what is the value of alpha? We got 0.434. Okay. Then we'll go back to the previous step. What is the previous step? Alpha by it's not ampere, I'm sorry. So alpha is a constant value. Okay, for, so what is the frequency now? So frequency is alpha by alpha by t on. So alpha is 0.434 divided by 2 into 10 power minus 3. Then what is the frequency you get here? Okay, please let me use this here, divided by 2. So into 1000, because we got 217. We'll see, am I correct? This, just check this. There is nothing else in there. Okay.
Correct, sir.
It's correct, yes? Yes,
Yes,
thank
sir.
you. Okay. So the frequency we got here. How much frequency we got here? Okay, the answer is the frequency is, okay, whatever we got here, we will write that. Okay. So 217 point, okay, 217.0 is there. So 217 hertz I will give. So this is for 400 RPM. Now similarly we will do for 800 RPM. How we will do for the 800 RPM? Okay, so we directly find out EB here for 800 RPM. Okay, how do you do that? So EB 1000 RPM is how much? 415 into 800 by 1000. So I think it is double the speed. So 166 into 2, I think. So okay, 332, I think. Yeah, 332. 332 volts. So we got EB at 332 volts. Then what is E naught? See, we are repeating that the same problem, so you don't need to worry much. So E naught is equal to EB 332 plus 50 into 0.5. So that is equal, it is 25. So 25 in the sense 357 volts. So 357 volts, that is E naught. Then what is, once we got E naught, what is alpha? Alpha is equal to 357 by 440. So 357. 3574. So 0.811. So 0.811. So we got this alpha value. Then what is frequency? Frequency is alpha by Tn. So alpha 0.811 by Tn is 2 milliseconds. So then divided by 2, okay, into 1000. So we will get 405. So the range of frequencies I will write here is that 2172 405. 217 to 405.68 hertz. Yes, this is the answer. That's it. That's it. This is about this problem. Okay. So now, once we got this simple problem, then we'll go to. So the same motor we'll take. The same motor we are going to take once again. Okay. So we'll take same motor here. In this same motor, we just okay. This time we'll go to second quadrant, regenerative control. Regenerative control will do. That is second quadrant. So same motor. There is no change here except the motor is now okay. Except the thing is now is that it's a regenerative control. So regenerative control in the sense it's the second quadrant. So second quadrant. So I will just now just recall the second quadrant. Last class itself we have done this thing, but anyhow. Second quadrant. Okay, so last class itself we have seen this thing, so we will not do all the things. Everything we have done already. This one because in the last class also we have seen this thing that the load also we have taken the same thing RALA only. So there is nothing much to do here more except one thing. One important thing is that what is E naught waveform we will get here. That is the more interested thing here now. Okay. This is E naught. E naught, yes. E naught. So now T on. This is T on, and this point is T. Okay, so this point is T. Now you see, this I told you already that when the switch is on, what is output voltage? Zero. This entire thing already we have done last class itself. That when the switch is off, that is from T on to T, then the diode conducts. This we have seen last class itself. Then E naught will become EA, and it repeats. It repeats. So this height is EA. Okay, then what is the average value of E naught? That's the question now. What is the average? How do you find out the average value? Okay, the area. Okay, the area divided by the total time period. So what is the area here? The area here is that yeah, right here A is the height. The breadth is T minus T on. Okay, whole divided by total time period. I will say like this because that is how do you find out the area. Okay, area divided by the total time period is the average value. So then E naught is equal EA into, so how do you write this? T by T, it is 1 minus T on by T, it means alpha. So this is the formula. I will rewrite this here once again, that E naught is equal EA into 1 minus alpha. So this is the relationship between input voltage and output voltage of the chopper when you operate in the regenerative control. Okay, that is this circuit diagram. So once we got this, then we'll go ahead with this once again. So E naught is the input to the motor. So input to the motor we can write like this: E naught is equal EV, okay, EV plus IA RA. So But one important thing you must understand here is that what is the actual current it is flowing now in this case of regenerative control? It is in the opposite direction of that. So I will take minus IA. So minus IA. Why I have taken minus RE, IA, RA? Because the current gets reversed here in the second quadrant. Okay, in the second quadrant, current gets reversed. This we have seen last class itself. So we got this answer. Okay, so then that implies EA into 1 minus alpha, that is equal EB. How can I write EB? I will write K into omega minus IA RA. Then now what is the torque equation? Electromagnetic torque. What is the torque equation you will get here? The torque equation here you will get is that what is the torque equation? That is K into IA. So here the K IA is negative here, so I will write minus. See here you should not get confused with the convention here. Okay. So what is the only difference here now? That equation still valids. Which equation? E naught is equal to EB minus IA RA. This equation still valids. So but only E naught is equal to EB plus IA RA. This equation still valid. Okay. Even though it valids, the only difference between the first quadrant and the second quadrant is that IA gets reversed. So when IA gets reversed, what I'm doing is that I'm not doing anything else except wherever you find out IA, I replace IA with a minus IA. Nothing else. I'm not doing anything. So then we simplify. We simplify this further. Okay. So then what is omega you will get? Omega is equal to EA into 1 minus alpha, E into 1 minus alpha, to E into 1 minus alpha by K minus what will get here? Minus or plus? We will get plus. We'll send this towards that side, so it will become plus. So sorry, once again you have minus only here. Minus you put here. Then because T is equal to minus K into IA, so IA is equal minus T by K. So minus T by K in the sense so just you need to cross check this. Only thing is that please cross check yourself that somewhere we get wrong, somewhere we get wrong or what. That is the only thing you can do. There is no other thing here. Okay, so we have to cross check that whether we went somewhere wrong or what. Okay, otherwise this minus plus signs are remains like that only. So we got, so only thing is that what we are doing is now we want to find out the relationship between omega and tau, nothing else. Okay, so now if we can find out omega and tau equation, then you see now. Then we draw the graph, just like how we have drawn the graph. Yeah, this I will take it as speed. I'm sorry, I will take it as omega, and I will take this as TE. That is minus this direction, minus direction. So I am taking all the T values are negative. First thing I am taking all the T values are negative. See, I have taken this quadrant, second quadrant I have taken. So the graph I am trying for the second quadrant because this operation is in the second quadrant. So now all the T values are negative. So it means, so you take any negative, so it is 0 is the maximum value, and after that you have all negative values. So if you take T is 0, then you will get some value of EA. So better I will take here, this point I will take here. Then after that what we find out, let me increase in the sense, let me increase the negative value in the sense, this value will get added up because T is minus 1 in the sense minus plus. it becomes plus. So we'll get something here, 1 point we'll get here, 1 point we'll get here, 1 point we'll get here. So what do you find out the graph? You find the graph like that's it. This is for one value of alpha. So for example, if I increase the value of alpha, what will happen? If I increase the value of alpha, okay, so then this point, this one, if I increase the value of alpha, what will happen? For example, I take 0.3, then I will take 0.7. Then in that case, this will get decreased. So I think this one. So increasing alpha. Just from the equation we are doing nothing else we are doing here. So increase the value of alpha, then definitely that part which I put in the box, okay, will decrease. You don't have any other option. So it will decrease that graph. So this is the speed torque relationship um, between for the motor, okay, which we are discussing here. Okay, then that's about regenerative